In the last lecture, I had described for you the characteristics of a turbulent flow. Okay. So, it occurs primarily at high Reynolds number when inertial effects are important, and that is because the inertial transport is nonlinear in the velocity. The quantity being convected, the momentum, is the same as the mechanism of convection, which is the velocity, and therefore, it is nonlinear. There are large fluctuations in the velocity in all three directions, and therefore, the flow is necessarily three dimensional. One cannot have two dimensional fluctuations in the velocity in a turbulent flow. The flow is highly diffusive because transport takes place due to the correlated motion of parcels of fluids called eddies within the flow of different length scales, all the way from the pipe diameter, the large scale, down to a small scale, which we will estimate shortly. Because this eddy transport mechanism is much more efficient than molecular transport, the transport rates, the dispersion in a turbulent flow is much larger than molecular diffusion, and for that reason it is also highly dissipative. Because the dissipation of energy, as I said, takes place due to the straining at the small scales, which is much larger than that for the large scales. I told you that it is a continuum phenomenon and a flow property. The equations, the vector equations for a turbulent flow are the same as those for a laminar flow, including the inertial, the viscous and the pressure gradient. It so turns out that the inertial terms turn out to be 0 for a pipe flow, for a laminar flow, for unidirectional transport, but the complete equations, the inertial plus viscous plus pressure gradient, those are the same for both turbulent and laminar flows. Since the equations are nonlinear, there are multiple solutions for these equations. One of these is the laminar flow, and then there are turbulent solutions as well. Okay. So, there are two types of solutions for the same equations, because the equations are nonlinear, especially at high Reynolds number, where the inertial effects are much larger than the viscous effects. And I had tried to explain to you the concept of stability and transition, okay. The concept of stability and transition. Okay. The distinction between a stable and an unstable, okay, equilibrium. Okay. In a stable equilibrium, in this particular one dimensional case, if you displace the system a little bit from its equilibrium state, it returns to its original state. If it is unstable, if you displace a little bit from its equilibrium state, it goes to some other state. Okay. Then there is a neutral state as well, where if you displace it, it remains at that location. Flows such as those driven by angular velocity, by rotation of cylinders, like the Taylor-Couette flow, okay, or those driven by natural convection, like the Rayleigh-Bénard flow, those actually become unstable. The equilibrium state becomes unstable, and the system goes to another state, which involves these convection rolls in a Taylor-Couette flow, or the circulation of fluid in a Rayleigh-Bénard flow. And as the parameter, the ratio of inertia and viscosity, or in the case of natural convection, the Rayleigh number, as that is increased, the system undergoes multiple transitions until it becomes a completely turbulent flow. In the case of flow in a pipe, the picture is not the same. Okay. There is no transition from a stable to an unstable state for infinitesimal disturbances, okay, as I have shown by the figure on the right. It turns out that the flow is unstable to finite amplitude disturbances. In other words, if the disturbance was below a certain amplitude, the system would come back to its original state. If it was greater than that amplitude, it would go to some other state. Okay. So, that is the turbulent the instability of a laminar flow. The laminar solution becomes unstable. This is a simple picture. The actual flow configuration is more complicated because the velocity is defined at each location within the flow, and at each location it has components in all three directions. Okay. So, basically we are looking at a flow, at a system which has a very high number of degrees of freedom, the velocity at each point, and each point different components. Nevertheless, the picture is still the same. In that high dimensional space, the system becomes unstable along one coordinate direction. I will not go into the details of how that is calculated, but that is the physical picture. So, in a pipe flow, it never becomes unstable to infinitesimal disturbances. It does the transition that is actually observed at a Reynolds number of about 2100, okay, is considered to be due to finite amplitude disturbances, and it is known that if you reduce the disturbances in the inlet and in the environment, you can maintain the flow in a laminar state at a much higher Reynolds number, okay, for the flow in a pipe. So, that is as far as transition to turbulence is concerned. What are the characteristics of a turbulent flow? So, first of all, it is highly dissipative. That means that the power required for a turbulent flow is much higher than that for a laminar flow, okay, or the pressure difference required for a turbulent flow is much higher than that for a laminar flow. Okay. So, the pressure difference across the ends of the pipe, okay, of length L and diameter D. Okay. The power required can be written as is equal to the difference in pressure times the volumetric flow rate. Okay. Let me just motivate this for you. If you have a pressure difference across the ends of the pipe, okay, the force exerted due to this pressure difference, the force exerted is equal to the pressure difference times the cross sectional area pi d square by 4. Okay. That is the force exerted, okay, on the fluid. Okay. The displacement in time delta t, okay, the average displacement of the fluid in time delta t is going to be equal to the average velocity times delta t. Okay. Therefore, the work done is equal to force into displacement, okay, which is equal to delta p into pi t square by 4 into V average into delta t. Okay. Okay, that is the work done, okay, within the time delta t. Okay. Okay. And therefore, the power, okay, is equal to work done divided by the time. Okay. The power is equal to the work done divided by the time, which is equal to okay, delta p into pi d square by 4 cross sectional area into V average. Okay. V average into the cross sectional area is the volumetric flow rate. Okay. So, that is the power required for driving the flow. Okay. And we know that the pressure drop for a turbulent flow is much higher than for the laminar flow at the same, okay, Reynolds number or at the same flow rate. Okay. Now, so this is the power required. Rather than analyzing the power required, we can analyze the intensive quantity, that is the power per unit mass. Okay. The power input per unit mass. Which will be equal to delta P into V dot divided by the mass of the fluid in the pipe. Mass of the fluid in the pipe is the product of the density times the volume. The volume is length into the cross sectional area. Okay. Volume is the length into the cross sectional area. Okay. So, that is the power input per unit mass, intensive quantity which we will use for analyzing the flow. Okay. Note that power has dimensions mass, length square, T power minus 3. Okay. Power is energy per time, energy is force into distance. Okay. So, from that you get m L square T power minus 3. Therefore, the power per unit mass is equal to L square T power minus 3. Okay. So, there is the expression for the power per unit mass. It has dimensions of length square T power minus 3. Okay. So, this is going to be equal to, note that this ratio, the volumetric flow rate divided by the cross sectional area. Okay. This ratio, volumetric flow rate by the cross sectional area, is just the average velocity. Okay. It is just equal to the average velocity. Okay. So, I will get delta P by L into V average by rho. Okay. So, that is the power input per unit mass. Okay. Now, I can use the friction factor correlation to express the pressure drop. Okay. I can use the friction factor correlation to express the pressure drop. Okay. You know that delta P by L, okay, is equal to 4 into tau W by D. Okay. And the friction factor is equal to tau W by half rho V average square. Okay. Okay. Is equal to delta P by L by 2 rho V average square by D. Okay. You recall that this was determined by a momentum balance across the ends of the pipe, where the force times the area, okay, where the force times the area. So, delta P, I am sorry, the pressure difference times the area. Okay. The force exerted due to the pressure difference, which is delta P into pi d square by 4, was equal to tau W into pi d L. Okay. The pressure difference times this cross sectional area was equal to the wall shear stress exerted on the wall times the cylindrical area. Okay. That was the force balance that we had used, okay, to get this expression. Okay. And that gave us delta P by L is equal to tau W into 4 divided by D. Okay. And this is, I should remind you, this is the fanning friction factor. Okay. This is the fanning friction factor. Okay. Therefore, in this expression I can write delta P by L is equal to 2 F rho V average square by D. Okay. I can substitute for the pressure difference in terms of the friction factor, and this expression becomes 2 F V average cubed by D. Okay. So, that is the power input per unit mass, okay, calculated based on the friction factor and the average flow velocity. Okay. Okay, so, let me remove these calculations. Therefore, the power input per unit mass increases proportional to V average cubed by D. Okay. As I told you, this power per mass has dimensions of, okay, the dimension of this is equal to length square by T cubed. Okay. And you can easily verify that this F is dimensionless, V has dimensions of L T inverse, and therefore, this has dimensions of length square per T cubed. Okay. This power input per unit mass, okay, also has to be equal to the rate of dissipation of energy per unit time, okay, per unit mass per unit time. Okay. This symbol epsilon is used for the rate of dissipation of energy per unit mass. Okay. That is the energy dissipated per unit mass per unit time due to fluid viscosity, due to fluid friction. Okay. So, therefore, this is a balance at steady state. The power that is put in through the pressure difference across the ends of the pipe has to be dissipated due to viscous effects in a turbulent flow at steady state. Okay. And this is the estimate for what is the amount of energy that has to be dissipated per unit mass per unit time. Okay. So, basically the production of energy, as it is called, the power input is called as the production of energy in a turbulent flow that has to be dissipated. So, production equals dissipation, okay, in a turbulent flow. Now, if you recall, I had said that in the turbulent flow in a pipe, there are eddies of various sizes in moving in all directions, a range of sizes, okay, fluctuating in all directions, okay, at all time. Okay. The largest eddies are of course comparable to the pipe diameter d. Okay. What is the size of the smallest eddies? The velocity of the smallest eddies in this case. Okay. The size and the velocity of the smallest eddies are estimated using what is called the Kolmogorov universal equilibrium theory. Okay. So, first things first, I told you that epsilon is equal to 2 f v average cubed by d. Okay. And if you recall, we had drawn the friction factor versus the Reynolds number graph. Okay. This is basically this is not friction, this is rather this is log. This is 16 by Re. Okay. It goes as inverse of Reynolds number up to the transition Reynolds number of about 2100, beyond which there is a much more gradual decrease, okay, in the friction factor. Okay. And the friction factor also depends upon the roughness. Okay. You get different curves depending upon the roughness. This we had seen earlier. Okay. Now, in a turbulent flow, the slope of the friction factor, the magnitude of the slope of the friction factor is much smaller than that for a laminar flow. Okay. So, it is usually assumed that this, okay, does not scale with Reynolds number. We can consider it to be approximately a constant. Okay. In which case, this energy dissipation rate per unit mass is estimated as V average cubed by d. That is the scale that is used for the energy dissipation rate per unit mass. Now, I told you that there are a range of different eddy sizes all the way from the large scale to the small scale. Okay. And the other thing that I told you was most of the dissipation of energy takes place at the small scales. What that means is that the rate of dissipation of energy at the large scales is much smaller than the rate of dissipation of energy at the small scales.
From there itself, sir.
Okay. So, I told you that there are a range of eddy sizes all the way from the large scale comparable to the pipe diameter down to the smallest scales. How small are the small scales? So, this is given by what is called the Kolmogorov universal equilibrium theory. Here it is assumed that the size of the smallest eddies and the velocities of the smallest eddies are so much smaller than the large scales that they are not directly affected by the large scale flow. Okay. They are not affected by the large scale flow, both the average flow and the large scale eddies. Okay. Because they are so much smaller, they are not directly influenced by the large scale flow, but rather influenced only by their local conditions. Okay. If that is the case, then the length and the diameter of these or the length and the size of these small scale eddies cannot depend directly on the average velocity and the diameter, but rather they depend on the large scale flow only through. Okay. On large scale flow only through the dependence on epsilon. Okay. They depend on the large scale flow only through their dependence on this intensive quantity, the energy dissipation rate per unit mass. Okay. Because they are so much smaller than the large scale eddies, the large scale the size is so much smaller than the size of the largest eddies, and the velocity is so much smaller than the velocity of the largest scale flow. They do not directly depend upon the large scale flow, but they depend only through their dependence on this energy dissipation rate per unit mass. So, it has to depend upon the energy dissipation rate per unit mass, and because all of that energy that is put in at the large scale has to be dissipated at the smallest scales. Therefore, the length and size should also depend upon the kinematic viscosity nu. Okay. So, therefore, the length, velocity and time scale for these eddies depend only upon epsilon and nu. Epsilon has dimensions, okay, we just calculated it, L square t power minus 3. Okay, the energy dissipation rate per unit mass. Okay. And nu has dimension length square t inverse, where nu is the kinematic viscosity, because that is what causes dissipation of energy at the small scales. Okay. So, the assumption here is that the length and the time scales and the velocity scales of the smallest eddies do not directly depend upon the average velocity and the pipe diameter, but rather they depend only upon the rate of dissipation of energy per unit mass with dimensions length square t power minus 3 and the kinematic viscosity with dimension length square t inverse. If it depends only upon these two quantities, then just using dimensional analysis you can estimate what are those smallest scales. Okay. Just using dimensional analysis you can estimate what are those smallest scales. Okay. So, the smallest eddies, the Kolmogorov eddies, okay, have to be have to scale as nu cubed by epsilon whole power 1/4. Okay. You can easily verify that the right side has dimension of length. Okay. Nu, the kinematic viscosity is length square T inverse whole cubed by length square T power minus 3. Whole power 1/4. Okay. And the numerator I have L power 4. Okay. When I cancel it out, the time scales cancel out, and therefore, this to the 1/4 is just a length. Okay. So, that is the length scale of the smallest eddies in the flow. What is the time scale? The time scale for the smallest eddies is, it has to scale as nu by epsilon, okay, power half. Okay. And once again, you can verify that this has dimensions of time. Nu has dimensions, L square T inverse, okay, and epsilon has dimensions L square T power minus 3 whole power half. It has dimensions of time. Okay. So, that is the time scale of the smallest eddies. Okay. These are called the Kolmogorov length and time scales. Okay. And the velocity scale of the smallest eddy, okay, scales as nu times epsilon whole power half. And once again, you can verify that kinematic viscosity has dimensions of length square T inverse into epsilon is length square T power, I am sorry, this is 1/4, my apologies. Okay. Into length square into T power minus 3 whole power 1/4 has dimensions of length T inverse. Okay. Okay, so, that has dimensions of velocity. Okay. So, based on the fact that the length, time and velocity scales of the smallest eddies, okay, depend only upon the rate of dissipation of energy epsilon and the kinematic viscosity nu, and they do not depend directly on the average velocity and the pipe diameter. Okay. We can estimate what are those smallest scales in a turbulent flow. Okay. What is the ratio of the smallest scales and the pipe diameter, for example? Okay. Okay. Is equal to nu cubed calculate it down. Times 1 over d. Okay. Now, I can write down that nu is V cubed by d. Okay. I can write down that epsilon is V average cubed by d. Okay. So, if I take the d in, I will get nu cubed by, okay, epsilon is V average cubed by d, okay, into d power 4 whole within to the power 1/4. Okay. And you can easily verify that this is equal to nu cubed by V average cubed d cubed whole power 1/4. Okay. Nu by V average times d is the inverse of the Reynolds number, okay, based upon the average velocity and the diameter. Okay. So, this is just equal to therefore, the Kolmogorov scale divided by the diameter goes as R e power minus 3 by 4. Okay. What is the Kolmogorov velocity by the average velocity? Okay. goes as nu epsilon power 1/4 by the average velocity. So, in this I can write nu times V average cubed by d, okay, power 1/4 times 1 over V average. Okay. And you can easily verify if I take V average into the brackets, I have V average power 4 there. So, this just becomes equal to nu by V average d, okay, power 1/4, okay, which is R e power minus 1 by 4. Okay. So, therefore, the Kolmogorov scale divided by the average velocity goes as R e power minus 1 by 4. And I can do a similar calculation for the time scale. Okay. The time scale for the large scale flow depends the average velocity and the diameter. Okay. The only way that it can depend on the average velocity and diameter is if the time scale is d by V average. Okay. The velocity is V average, d is the diameter. Therefore, for the large scale flow, d by V average is the time scale. Okay. So, if I take Kolmogorov time scale by d by V average, okay, I will not go in through that, but you can easily verify that that is equal to goes as R e power minus half. So, the length, the velocity and the time for the Kolmogorov scales divided by their corresponding values for the large scale all are proportional to a negative power of the Reynolds number. Turbulent flow is a high Reynolds number phenomenon. Therefore, the smallest scales are much smaller than the large scales in a turbulent flow. So, this is a part of the picture of turbulent flows. In the next lecture, I will continue this and look at other quantities, the kinetic energy, the strain rate and so on, okay, based upon this Kolmogorov universal equilibrium theory. Okay. So, I will continue this discussion in the next lecture. I will see you then.